In this work, we propose a new spatially correlative loss for ensuring structure consistency in various image translation tasks. In a translation task, we aim to transform an image from one domain into another, such as horse to zebra, but we do not have paired data for training. The GAN loss is often used to encourage the new appearance to fit the target domain. However, we also want to retain the geometric structure of objects as much as possible. How can we model this in a more explicit manner than previously done? The existing works either use cycle consistency loss in a two-sided framework or other forms of pixel level and feature level loss in a one-sided framework for preserving content. However, the former cannot provide explicit constraints. The translated image can be arbitrary shapes, while the latter one cannot disentangle the structure and appearance due to the different appearances naturally hold different features. We often see patterns of self-similarity in images. Consider these stars. They have different appearances, so naturally, the neural net features are also very different. But we can obviously see they have the same shape, so how do we capture this? Our key insight is that the stars all share the same spatial patterns of co-occurring signals. For each image, we can construct a self-similarity map to represent scene structure. So if two images look completely different but have identical scene structure, we expect them to have the same self-similarity maps. Suppose we already have an image and a corresponding translated version. We first extract features using a pre-trained network. However, these features hold totally different values in the corresponding channels. We then compute feature self-similarity maps at a number of locations in both images. Our spatial correlative loss measures the difference in corresponding self-similarity maps, which captures the difference in scene structure between input and translated images. While the fixed version have achieved excellent performance on some tasks, we further explore a learned version using a form of contrastive learning. Given some extracted self-similarity maps in patches, the FLSeSim explicitly encourages same structures to be closer, regardless of their appearances, and associate dissimilar structures, even they have similar appearances. Note that this contrastive loss is only used for training the feature extractor to obtain better structure representation. We can also visualize the self-similarity maps in different layers. While the horse and zebra have very different textures and colors, notice how they share similar repeated patterns of self-similarity in the deep layers. Hence, we can select the suitable self-similarity map as the spatial correlative loss to ensure structure consistency during the translation. We evaluated our spatial correlative loss on many translation tasks, including single-modal and multimodal translation. This loss can easily be plugged into current state-of-the-art frameworks to directly improve results without having to change network structures and training parameters. Here, we only replace the original cycle loss with our proposed content loss. We improve the performance, such as horse to zebra, semantic to image, night to day, and winter to summer. We further show that our spatial correlative loss works well for single image translation, such as paint to photorealistic image. Thanks for your attention. More sources are available on our website.